Good morning, good afternoon, or good evening, depending upon where you are in the world, and welcome to today's webinar, High-Speed Board Design Guidelines, brought to you by Tech Online, MoSys-Arrow, and broadcast by AspenCore. I'm Chris Keach, and I'll be your moderator today. We have just a few brief announcements before we begin. First, the slides will advance automatically throughout the event. You may also download a copy of the slides by clicking on the green folder icon located at the bottom of your screen. You can participate in our Q&A session by asking questions at any time during this webinar. Just type your question into the Q&A text area located to the right of the presentation window and then click the Submit button. Please note that we'll try to get to as many questions as we can during the time that we have left at the end of today's program. However, if we're unable to get to your individual question today, someone will get back to you after the program is over. Also at this time, we recommend that you disable your computer's pop-up blockers. And at the end of the webinar, we will ask you to complete our feedback form. Your feedback will provide us with valuable information on how we can improve future events. You can also launch the survey at any time by clicking on the red survey button at the bottom of your console. And if you're experiencing any technical problems, please type your issue into the Q&A text area, and we will be glad to offer one-on-one assistance. And now, on to the presentation, High-Speed Board Design Guidelines. Discussing today's topic are Mark Baumann, Director of Product Applications at MoSys. Mark has been at MoSys for over 10 years. He held previous positions at IDT, Avago, and NetLogic, and he has spent most of his career working with various forms of high-speed memory. And joining him today is Gus Lignos, VP of Worldwide Sales at MoSys. Gus has been with MoSys for 11 years, and he is responsible for worldwide sale of all products, including ICs and IP. It's with great pleasure I now turn this special session over to Gus to begin. Gus, take it away.
Thanks, Chris. Hello, everyone. Thanks for joining us. I want to give you a very quick overview of MoSys. MoSys has been around since 1991. We were a spin-out from IDT, and the company was selling IP in its early days, selling 1T SRAM, which is the building block for the EDRAM process at TSMC. It's a very efficient, high-performance piece of memory IP that is embedded in semiconductors. And TSMC had been selling that in multiple process nodes for many years, and the company decided to transition from being strictly an IP company to becoming a fabless IC company, leveraging that IP. So we took that 1T SRAM, very efficient memory block, and we bought two SerDes companies, one for high performance, one for low power, and created a family of ICs called a bandwidth engine, which is a very high speed and efficient way to get data in and out of your host processor. So we took away that bottleneck in getting to off-chip memory by interfacing to the host, whether it be an ASIC or an FPGA or an NPU via SerDes. So very efficient protocol. We created it called Gigachip Interface, GCI. It's an open standard, and it's just a simple way to get memory in and out for high-speed processing. As data rates go up to 100 gig, 200 gig, 400 gig, it becomes a bigger and bigger bottleneck, and we solve that with this family of products. We're on our third generation of bandwidth engine products. The most high-end device has 32 embedded RISC cores in them. They're our own design. They're MIPS-like. We had a lot of CPU architects, and we built those cores. And then to showcase what you can do with this high-end device, we created some IP in the form of firmware to do some search functions. And in talking to customers, they really liked it and said, you know, this IP is really good. Is there any way you can extend that down to be IP we could buy and use in either FPGA or ASIC? And we did that. And we introduced a family of products called Stellar IP. We have a lot of cosmic names like Blazar and Quasar. So the IP is a packet classification family, including LPM routing IP and exact match IP and high complexity ACL IP. So it's often used to replace TCAMs. Instead of using external TCAM, you can embed this IP in your FPGA and leverage your on-chip memory or external DDR or HBM. And so we're now in two product families. Again, we're selling IP, which is used for search, and we're selling high-speed memories, the bandwidth engine family of products, and Mark will get into how to design with those products. And when you think of the bandwidth engine family, think the speed of SRAM with the capacity of DRAM, leveraging a very efficient chip-to-chip serial protocol. And with that, I'm going to turn it over to Mark Baumann, our Director of Applications.
Okay. Well, thanks, Gus. Hopefully everyone can hear me. I, too, want to thank everyone for taking time out of your day to join us here today. What I'm going to do is, obviously we had a bit of an intro to MoSys already from Gus, so we'll speed through that. I want to go over some of the terminology that we'll be talking about today, and then get into some of the guidelines that MoSys has come up with. And again, these are very common. You'll find guidelines similar to this from all the large semiconductor companies that deal with high-speed signaling. So you'll see a lot of things that are common across the industry. We'll talk a little bit about crosstalk and the issues of crosstalk, layout, and again, because as Gus pointed out to you, we're a company that is based our devices on a SerDes I/O structure. So all the MoSys I/Os are SerDes based at a minimum of 10 gig, and we go up to 25 gig. So
and Mark,
we'll talk a little bit about those.
Mark,
yes. Yes.
Mark, I'm sorry to interrupt. Yes. One thing I forgot to mention in my introduction, MoSys also has a family of 100 gig PHY ICs. You know, we talk about having a lot of SerDes expertise, and I was remiss. We have a family of gearboxes and retimers similar to the products that you might be familiar with from Broadcom and Marvell. So I want to throw that out there as well. So there's two IC families, the high-speed memory with the serial interface, and then 100 gig PHYs based on 25 gig NRZ, SerDes, and then, of course, the packet classification IP. Back to Mark. Thank you.
Okay. Thanks, Gus. And then finally, we'll talk a little bit about power integrity as well. So this is what Gus was talking about. There are the serial I/O memory products that we offer, and that's the Quasar, Blazar families. There's the line speed family, which Gus just mentioned about all that have gearboxes and retimers. And then we have our Stellar IP product. What we did, I just wanted to show you a rough block diagram of some of the products that we have, the IC product. And again, it's a large memory device. And instead of the multiple hundreds of pins of parallel I/O, MoSys realized that the trend in the industry was to go to a SerDes I/O structure. And that has played out. You can see it on all the Intel and Xilinx FPGA families and ASICs that you see in ASSPs. There are hundreds of SerDes lanes that are being built onto these products now, and less parallel I/O structures. And you can see even with the Intels and the Xilinx of the world, the parallel I/O structure going internal. Talking to things like HBM, the high bandwidth memory, is now a wide internal bus that just talks chip to chip and doesn't go off board. So we realized that talking externally was going to be a SerDes-based world in the future. So again, one of the things we wanted to do was, they always say, eat your own food kind of thing. We wanted to actually say, okay, if we think SerDes work on a structure, maybe we should build our own boards and see how it is to do that, how hard it is to do that. So we've built a series of these boards now, maybe 10 or so boards that have that FMC, the FPGA mezzanine connector, I/O structures. And we've built them to interface to all the Intel and the Xilinx, characterization cards and things that they put out in the market. So again, we have actually done this work. we wanted to make sure that it's a viable product when you do something like this to talk to a memory. So at this point, I believe I'm going to toss it back to Chris just for a moment to ask a first polling question.
All right, thank you, Mark. We have several polling questions for you today, and the way to participate in our polls is simply click on the radio button next to the answer that's appropriate for you, and then click the submit button. So our first question here for you, do the designs you were doing utilize SerDes? Your answers here can be no, yes, 10 gigahertz to 15 gigahertz, yes, 20 gigahertz to 28 gigahertz, or yes, greater than 28 gigahertz, for example, 56 gigahertz to 112. And so just go ahead and click on the radio button next to the answer that's appropriate for you, and then click the submit button. We'll take a look at those results here momentarily. We want to give everyone an opportunity to go ahead and answer that question. And then also, if you have questions for our speakers, just go ahead and click on the Q&A icon, type your question in, click the submit button. We'll get to as many of those during our Q&A session at the end of the program as is possible. If we do not get to your question today, again, someone will get back to you after the program is over. So let's take a look now at some of our results and see where we are. It looks like about 49% said no, and 32% said yes for the 10 to 15 gigahertz range. About 12% said yes for the 20 to 28 gigahertz range, and only about 6.1 said greater than 28 gigahertz. So Mark, what are your thoughts on our polling results of the first poll?
Yeah, no, I think that's actually what I was expecting, and I appreciate hearing that because I'm glad the topics that we'll probably talk about today are a little more geared toward the lower three, you know, the no, 10, and 20. The people who are familiar with 56 to 112 gigahertz, you know, this kind of conversation is more everyday structures that they go through. So it is a guideline. We're trying to go through guidelines of things that we look for when we're dealing with high-speed signaling like SerDes. So that's really good. I'm glad to hear that this is the way the characterization of people is falling out here. This should be good. Should be a good conversation then. So I'll move on and tell you some of the issues that we're going to talk about here. So terminology, and again, when you look at PCBs, printed circuit boards, there's ways of running etch, right? So you'll have microstrip, which is etch that's physically run on the top or the bottom of the board. So it's not an inner layer. And then there's strip line, which is the internal layers and the etch that you run there. Those are the etches that most of these high-speed signaling are going to be run on. And the obvious reason for that is you can see there's a ground on or a plane that runs on top and bottom of that. And if you think about it, you're kind of building your own little coax cables on the internal layers of the PCB. So that's kind of why, you know, most people use the strip line, although microstrip has its own benefits. You then don't need to go through the vias. That is the next big thing we'll talk about. And vias obviously can be a source of great discontinuity in how you route signals across boards. Right, so if you think about the etch, it's just going along a nice straight line, and all of a sudden you have to say, I'm hitting an obstacle. I have to change layers. I have to go down or up into a different layer. You go to a via, and you know it's a totally different structure, right? It's a circular structure that you have to land on with some kind of landing pad. And then you go up and down, and there's when you think about signaling, it's the edge of the signal that really causes a tremendous amount of issues in routing, right? It's not the DC portion of the signal, it's the edge, the rise and the fall times that are going to be of issue. So when you have that, any source of capacitive or inductive discontinuities or changes is going to cause a tremendous amount of dispersion within the signal itself. And then there's options. You can see the right-hand side there. There's these through via, blind vias, and buried vias. And those are all options for printed circuit boards. Obviously, the through via is the most common and the least expensive of them. The others take a lot more technology to make sure that they align properly, everything is connected properly. So there's a little more expense associated with blind and buried vias. The one thing I wanted to point out, and we'll talk about it a little bit more later on, is that even on the through via, there is the possibility, if you look at the bottom of the diagram there, it says back drill. That is something that has become very common with very high speed signaling. And if you think about it, you don't want this little stub at the bottom of the via. If the signal doesn't need to go to those bottom layers, you don't want the stub of the via tube there to be part of your signal trace. Could cause all kinds of things like reflections and issues that you don't want to deal with. So there's some other terminology we'll talk about, insertion loss. This is just physically the insertion that's suffered from putting a signal onto your trace, onto your channel. So it's a ratio of the output signal to the input signal. Okay. Now, insertion loss sounds like it's a negative, and in many ways it is. But you also want to think about the design of a driver, in this case a SerDes driver. It has to be, when they're specified, they're designed for a range of conditions under which you might place them. So insertion loss is not necessarily a bad thing. If you design a driver to drive over, let's take the MoSys case we designed for driving somewhere in the order of 10 inches of etch. So you might have, 12 dB or something of etch that you can live with. And all of a sudden you design a board and you put your devices literally less than an inch away. We've had this happen with some customers of ours where they physically can jam a lot. Everybody wants to put 10 pounds in a 5-pound package. You can put a lot onto a card, and they put them very tight together. Well, that etch is almost non-existent. It's less than an inch long. But we still have a driver that wants to drive 12 inches or 10 inches. So putting a bit of insertion loss is not necessarily a bad thing. And so that, you certainly want to design for it and live with it when you're doing your PCB layouts. Return loss, on the other hand, is not necessarily as nice. Again, it's reflection caused by discontinuities in the transmission lines. Right? So return loss is something that you definitely want to try and minimize and design for. Some of the tools that are available use things like S parameters, which is a scatter parameter that characterizes your network itself, actually the etch and things that you're traveling across. And it will look at the currents and voltages that are affected with any discontinuities like a via that you might come across on your line. And one of the more common S parameters you might hear of is the S21, which again is insertion loss. So if you hear that term, it's the signal received at the second port from an insertion of the signal at the first port. So if you're thinking about a transmit to a receiver, it's the receiver's what the receiver gets from the input from the transmitter. Again, just channel. Again, I want to reiterate that the channel is more than just the etch. The channel that you're going to consider really has to think about the package even that the device is in, and the bumps and the balls associated with the package and the etch on the package, and how it's even routed, how signals are routed in the package. Then if you have any connectors, certainly there's huge discontinuities potentially with connectors, and how the trace runs to the connector and through the connectors themselves. And then all the way back out to the receiver and the reverse on the receiver side, the full package, ball, bumps, everything. Crosstalk is another one of those things that is of concern with very high-speed signaling, and that is the unwanted transfer of signal between channels. Okay, so the way that we'll talk about handling crosstalk again is how you lay out your PCB and considerations there. All right, so the first thing that we'll talk about in consideration is the actual PCB material itself. That is one of the initial things that you'll talk about when laying out a PCB. And what you want to do is select material that has lower loss, so it'll reduce the signal attenuation that you see. All right, you want to use lower dielectric constant with flat frequency response. These are the kind of things that you'll ask for, and it will reduce the signal dispersion. So, and dispersion we mean by anything that impacts the speed and transmission of the signal through the channel. So it'll reduce that dispersion because that adds phase jitter into your signals, right? And phase jitter is going to be reducing your, because we're talking SerDes, it's going to reduce your eye openings and things like that. And there are some very unusual little things that, some people don't think about, and that is even the fiberglass that's used in the PCB material itself. The density of the weave of the fiberglass actually makes a difference. Because if you have a wide weave, then when you look at the surface of the fiberglass, there are slight indentations in between the fiberglass and the prepreg that makes up the PCB itself. So again, choose dense fiberglass, and then the other thing is the way they deposit copper onto the fiberglass is either with a foil or electrodeposition. It's nicer to have the foil only because the foil has a surface, does not have as much surface roughness. And with high-speed signaling, what you get is the skin effect. So again, the current travels toward the outer edge of the copper itself. So what you want to do is have a nice smooth surface for it to travel through. Here are some of the higher end materials: Nelco, Rogers, Megtron 6. These are some of the higher end materials that you might see if you're selecting for high speed signaling. And again, what I wanted to mention is that it's very, very possible and common that you use these higher end materials just for your high speed signaling. not necessarily for everything. So you can intermix these higher end materials with the regular FR4 materials. The other thing that you want to do is try, it's a good rule of thumb just to be as conservative as you can as the layout lets you be. So you want to try not to narrow down your trace width. For many high-speed signalings, you want something in the 5 or 6 mil wide range. Narrowing it down to 4 mils, which quite often you have to do for things like escapes from very dense BGA packaging. You'll have to go from an internal ball to an to escape the routing out to the outer layers, and so that forces you to have minimum width signal traces. You want to minimize the amount of time that you're doing that. And again, you can create discontinuities or when you narrow it down and make it harder, you can actually have more dB loss. We noticed that for a 28 gig signal, and most things you measure at Nyquist, which is half the high-end frequency range, so at 14 gig, you'll get an additional 3 dB loss over a 4 mil trace versus a 6 mil trace. So it's a real measurable impact to be, again, try and be as conservative as you can when you're doing signal layout. Okay, and then again, success is just successful data transmission across the link. That is success. Where it can function for a reasonable amount of time. So if we have this thought process of what's close to ideal, non-ideal, and risky, and you can see the relative width. So if we're talking again about strip line kind of routing here, where we have signals on inner traces. And the ideal thing you want to do is kind of build an isolation for the routing that you get across the board. So the ideal thing would be have signal traces, but they're surrounded on tops and sides by some kind of grounding. Again, that's ideal. Not everyone has that luxury to have ideal routing. Non-ideal routing, very common and also very good routing, is to tighten it up and have only a ground separating the maybe your P and N pairs that you have for routing on PCB. The riskiest one, obviously, is you don't see any ground. And again, what you're suffering, even though there's some separation there between pairs of traces, is this, you have a mutual inductance and capacitance and coupling that you're going to suffer even with some separation. So it's always better to put some kind of grounding. And again, this is just kind of putting more words around that same idea, what you really want. What I wanted to show is kind of pictures. So you can see up on the left-hand side there, that pinkish route, that brown area would be grounds. So it's nice wide traces. The traces run parallel to each other. There's nice smooth turns. You don't use 90-degree turns or something on routing the trace. That's a really nice way to lay out a board. The one that says non-ideal with the little green traces, you can see there's actually kind of an ideal trace on the left-hand side of that picture. And on the bottom part of it, what we're calling non-ideal is this simple fact that you'll have to narrow down some of those internal traces to route it out and get it out to the outside of the outside the BGA area that to widen the trace back up. So there's an area that you're probably running narrower trace. And again, you just don't want to minimize that trace any more than you have to for if you can route it back out to 6 mil trace. And then there's bottom one, which is risky because you can actually see there's actually no grounds associated around these traces. They're all similar to the non-ideal, but there's no grounding separating, like the blue grounding in the non-ideal and the brown in the ideal. So again, grounding, what you want to do is make every effort to make everything as uniform and consistent as possible. I think we have another poll question now. I might turn it back over to Chris again.
All right, thank you, Mark. We do have our second polling question, and this is our second of what looks like 3, possibly 4 polling questions for you here. Our second question for you: has the use of SerDes been related to large packet transfer functions like Ethernet, TCP, FTP, MDP, etc., or protocols like intertaken? Here your answers can be packet transfer or chip-to-chip. Just go ahead and click on the radio button next to the answer that's appropriate for you, and then click the submit button. And as a reminder, if you'd like to ask a question, now is also an ideal time to do so. Go ahead and click on the Q&A icon, type your question in, then click the submit button. We'll get to as many of your questions as is possible at the end of today's program. However, if we're unable to get to your individual question today, someone will get back to you after the program is over. So again, we'd like you to participate in our second of what looks like 3 polling questions, and click on the radio button next to the answer that's appropriate for you. Click submit, and we'll move on here in just a few minutes after we get, or a few moments I should say, after we get our results. So let's take a look now at what we have for results. Looks like about 35% actually said packet transfer, and chip-to-chip was around 65%. So Mark, your thoughts on our second polling question?
Yeah, that actually surprises me. I was expecting it to be actually the opposite, and that's really great because there are different considerations associated with chip-to-chip concerns versus packet. Packet transfers usually have to travel over backplanes, and you know, they're long distance things. Chip-to-chip, we're literally talking on a PCB point-to-point. And there are different considerations associated with that and different concerns. One of them being the protocol itself that's used. We developed, as I believe Gus pointed out, a Gci protocol, and what we did that for is because chip-to-chip, you're certainly not going to suffer as severe an environment as you would having to go across a backplane and transfer of large packets. So we actually have developed a protocol that's very lightweight, but still gives you the security of a retransmit and being able to resend signal if you have any issues with it. So it's been unusual to have people do the chip-to-chip protocol as a higher priority, as a more experience than a backplane or an Ethernet kind of thing that's going on. So that's good. That's great. The next thing we'll talk about here quickly, because I know time is marching on, is VIA design. One of the things I think we mentioned right at the beginning is VIAs are very important because it's very rare. And again, if you're using microstrip, the benefit of the microstrip would be that you keep it on one layer. You keep all the routing you want on one layer. You might be able to actually come right off the ball of your PCB that you're putting down on the board, route a signal on the upper layer all the way to the receiver. And then you don't have to go through a VIA, right? So ideally, you know, that's the real benefit of the microstrip. The strip line, however, you're going to have to go through a via, right? You have to go down to those lower layers to talk to get onto the trace. So, and there's every chance for a discontinuity there. The via impedance tends to drop down to 80, 85 ohms versus the ideal 100 ohm differential that you're trying to keep. So there is a discontinuity that's going to happen. And there's issues of both capacitance and inductance that will change based on how you route. So again, what you want to do is reduce the via capacitance that you're going to add on by reducing the size of the capture, that landing pad that the ball of the BGA is going to land down on. And then there's you want to make sure that internally there's no non-functional pads that may exist. You want to clear those out, and again, minimize any discontinuities of the trace to the via itself. And then there's this anti-pad, which is the clearance that you're going to have around the landing pad itself. You want to increase that to 40 or 50 mils. So again, it spreads it out. You're not getting as much capacitive effect associated with the trace around it. And again, the inductance, we talked about that idea of back drilling. And again, what we want to do is minimize the via barrel length, right? You want to really, that's where the benefit of those buried in blind vias. They're really nice for minimizing things like inductance and capacitance, but they're a more expensive process to do. So it's hard to find, it's hard to justify that sometimes. And you can minimize the length of the barrel by just back drilling, literally taking a drill and drilling out the extra stub of the via. So then again, what we'll talk about is the actual signal trace and how you would do this. What we found is important as far as matching pair. You really want to match the differential pair as closely as possible. And this is the P and N lines that, the differential for the SerDes traces themselves. And it's not as critical to match a TX to an RX. And you can even see that with so for a SerDes lane or link, you're going to have a transmit, and the transmit pair is going to be P and N, and then you're going to have a receive P and N as well, right? So it's not as important to necessarily match the transmit and the receive because they are their own pairs, and but it is important to match the P and N of the transmit and of the receive pairs. And even in the MoSys devices, what we did is to actually separate any coupling from the transmit to the receive, we actually put the transmit and receives on opposite sides of the die. So it is something that's very doable, and you can consider separate paths for each. And then again, we talked about even with perfectly matched P and N pairs, there's non-uniformity in the materials themselves that could affect the signal, right? And there might be some coupling associated with that. So again, we talked about escaping from the PCB. You might have, escaping from under your BGA device itself may cause some difference in routing because of that. And what you want to do is match those back up as soon as possible so that everything runs uniformly and together. In data rates that we deal with in the MoSys devices between 10 and 28 gig, we shoot for matching the length between a P and an N to 1 mil. And with all the new PCB layout tools that exist today in the world, that is not that difficult to do. So that's a very achievable kind of task to undertake. What I wanted to just show here is again this matching of length, right? So once the tool actually goes and matches, you actually do an initial route. You can then get a printout, or it'll show you the actual trace length very accurately, and you can see whether your P and N are matched properly. And you can see the one that has these little yellow arrows to it. There's quite often a mismatch in the physical length between two traces, and what they tend to do is put this little wiggle pattern into the shorter path to lengthen it up and match the longer one. The thing you want to do with that is do it as close to the point of the original mismatch. So as close to the PCB, the BGA material itself where it occurred. So that's ideal. And you can see the one that's just to the right of the one with the yellow arrows, where the wiggle pattern is much further up on the trace. It's certainly a doable thing, but it's not ideal. What you really want to do is try and match that pattern as close as you can to the source of the discontinuity as possible. Another trick to play with that you know about is reversing polarities. It's not necessary. Most devices these days can recognize the P and N and actually reverse that for you. So it's not necessary that the transmit P go to the receive P. It's possible that the transmit positive can go to the receive negative. And you know, with a lot of the initialization routines that SerDes have in them, they can recognize there's an inversion and actually compensate for that. So if it makes sense and is better for routing, that it's very possible that the routing a transmit positive to a receive negative is fine in most cases. So that's another trick that you can play to minimize route length and try and keep things as uniform and parallel as possible. Another very common issue that you're going to come across is with SerDes devices is AC coupling. This is what you want to do is make sure that you don't get any offsets. There's a specification called CID, the consecutive identical digits, where there's a possibility of a DC offset that would happen on some traces on the SerDes. So what you want to do is essentially put an AC coupling cap in the path to minimize that. Most cases you'll put it as close to the receiver as you can, but it's not necessarily has to go there. But and the other thing you want to do is you want to match the capacitor size to the trace width. Again, because all these points of discontinuity could happen in the actual routing of the channel itself. So there are games you play because it's very possible that even a size in 0201, which is a pretty small capacitor, the landing pads and things associated with that are going to be larger than the trace itself. So you'll have a capacitive discontinuity caused by that. So you can play a game of making, opening the etch under the capacitive landing pad so that you don't have additional capacitance due to the pad itself. And so those are some of the games that you can play with, the routing and the AC coupling caps, which are very common in high-speed systems. And when you get into the higher end, even the capacitors themselves are multi-terminal capacitors, more than just the two, and you'll see there's additional games that have to be played at 56 and 112 gig. The next thing, one of the last things we'll talk about in general is power integrity. Obviously, power is very important in PCB routing. And the one thing you want to make sure is you get as much plane, an uninterrupted plane as possible. The power planes in PCBs are, they're trying to, again, we're all using multiple VDDs on devices now. You'll have 3, 4, 5 different VDDs going to a device. But the planes that deliver the power to the device, you want them kept as solid as possible. You don't want to cut them up. And so that's an important issue to try and undertake, even if it's multiple layers down. If you can keep as big a plane as possible, that's important. The next would be capacitors. And in most cases these days, I think if you look under any of the FPGA boards that are put out by Intel or Xilinx or anybody that's out there, people are putting capacitors literally under the device itself. And we kept the ball out of the MoSys devices at 1 mil pitch so that you could physically put a capacitor under the package, and you'll see that the ball out pattern that a lot of places are using allows like a diagonal connection between a power and a ground to actually put a small capacitor in there. So what you want to do is just minimize the amount of inductance to the capacitor so that it can deliver the current it needs to without any impedance in the way. So that's why people are trying to put capacitors directly under a device. The other thing that you want to see, probably you can't find this out, but what the DIDT of the supplies might be, that's always hard to do because you just don't know the use patterns and worst case patterns you might come up with. So those are very, very, very difficult to understand. So the safest thing to do is use a range of capacitors, right? You want to use different decoupling capacitors. You want some bulk decoupling, and then you want some high frequency decoupling as well. So that's where you'll end up with a series of these, 100 mic to 0.01 mics to, some bulk decoupling caps. So again, this is, I'll be really quick here. I know I'm using a lot of time. The bulk caps, so you'll do bulk, you'll do tantalum, you'll do large capacitors. So and again, those tend to be a little further away, but their frequency response is not as high usually. You don't have to deliver very high frequency response off of a tantalum cap, let's say. So the distance from the source is sometimes not as critical to where you place those caps. The other thing, though, and it's very common in devices that use SerDes, again, you may have multiple power rails, and the power rail that you use for the DC or the digital component of the circuit may be the same value. Let's say you have a 1.5 volt supply. You may use 1.5 volt supply in your digital portion of your circuit, and you could also use it in the analog portion of the circuit. Well, again, you don't want digital noise coupling onto your analog power rails. So it's common sometimes to use ferrite beads actually to isolate and make sure that there's no coupling between the digital and analog. You can use the same power supply, but you want to isolate the two supplies. So again, you'll check if the DC resistance is low, so that the power supply voltage levels are within tolerance of the two. So it's possible to even see things like ferrite beads when you're using analog and digital circuitry on a card. And again, if you use senses, if you do use sense lines from your supply, make sure you connect those as close to the load as possible. That's where you want to sense any variations in the actual power rail itself. I'm going to turn this back over to Chris just again briefly for our last polling question, and then we'll wrap it up.
All right, thank you, Mark. We have our third and final polling question for you. And our final polling question for you says, are you directly responsible for PCB design, or is it outsourced to a PCB design house? Here your answers can be, I'm directly responsible, or I'm responsible for providing guidance. Oh, hold on one sec, somehow we jumped there. For providing guidance to a PCB design house. And go ahead and click on the radio button next to the answer that is appropriate for you. Click the submit button, and then we'll be moving on here shortly to your questions. So now is an ideal time to go ahead and ask a question if you have one. Go ahead and click on the Q&A icon, type your question in, click the submit button, and just as a reminder, we'll get to as many as possible. If we're unable to get to your individual question today, someone will get back to you after the program is over. So we'll wait a few more seconds for everyone to input an answer, and then we will move on with the program. So let's go ahead and take a look at our results now. It looks like about 71, 72% said I'm directly responsible, and the rest said that they go ahead and provide guidance to a design house. So Mark, your thoughts on our final poll.
Okay. Yeah, no, again, this is exactly opposite of what I would have expected. I feel a lot of even large houses, large development houses that we've dealt with actually use PCB design houses actually to do this rather than try and undertake the actual PCB design itself. And they supply a set of guidelines, which is kind of what we're walking through here today, to the PCB layout house, and let them undertake some of the rules to do this. But that's really interesting that everybody is actually directly responsible for the PCB design themselves. That's again, not what I would have expected, but I appreciate understanding. So this should, again, this information, it might be old hat to you in some ways, but it's really important to us as users to understand, how this is done and what to look out for. I'll tell you, we even as a process at MoSys, we do a lot of reviews associated with PCB layouts around the MoSys device. So again, around the SerDes layouts and the PCB, the power layouts associated with the MoSys device itself. Using some of the Allegro tools and things, just the visual visual inspection is really an important tool that we've used, again, for helping out and just understanding what's going on. I can see my time is ticking down to a really short amount, so I'm going to really be fast here. These are some of the considerations that we have. Signal attenuation is certainly important. Any kind of discontinuity, crosstalk, and again, you're going to have this. The biggest thing to handle with crosstalk is just how do you route the signal traces themselves. Again, you're going to have either microstrip or strip line, and what you're going to have is this dispersion associated with signals that are close to each other and that are going to couple onto each other. So that's really the things that we pay attention to when we're looking at and even defining our PCBs that we had built at PCB design houses. That's the guidelines that we provided to them. So again, use the bottom line that I guess I want to say here, and I'll be quiet, is to be as conservative as you can along the way. Use robust traces, 6 mil traces when you can, 4 mil traces at a minimum. Try and keep everything constant between the two P and N's, and then again pay attention to everything from the clearance that you have around vias all the way down to the DC coupling caps and things that you use. Every place that potentially a discontinuity can happen. The next 3 or 4 slides are just kind of a checklist that we tend to use on when we do layouts and checks ourselves. So I'm going to allow not a lot of time, but allow time for maybe an answer or two to any questions you might have. And again, I really want to thank you for your time. And if there's any questions, again, there's some contact information here for Gus and myself that we could potentially answer any additional questions as well. Or you can get in touch with your Arrow contacts as well. They know how to get in touch with us.
All right. Thank you, Mark, and thank you, Gus, for a great presentation. We're going to now move on to the question and answer portion of our event. But first, as a reminder, please fill out the feedback form that will open up at the end of the show. Thank you in advance for filling out the feedback form. Your participation in this survey will allow us to better serve you on webinars in the future. Again, we're now moving on to the question and answer portion of our event. If you'd like to ask a question, simply click on the Q&A icon, type your question in, click the submit button, and we'll get to as many of these here in the few minutes that we have left as is possible. And it looks like we're going to go just a couple of minutes over, so please stick around. And our first question for you, Mark, or for Gus, depending upon who gets this one. Do you recommend necking down high-speed trace width only in the breakout area and then increasing their routing width to reduce loss of Skinner traces, even though this creates a discontinuity?
Yes. In our case, in the examples that we've done, yes, we want to minimize the amount of time that the traces at that 4 mil or the minimum trace width, and then widen it back out as soon as we can, and then try and balance it again lengthwise by doing that wiggle pattern kind of thing. But that's
all right. Thank you, Mark. Thank you, Mark. We'll move on to another one here for you. If you're grounding between if grounding between traces can't be tied back to the BGA, for example, the traces are too close, is it okay to start grounding between traces once traces are farther from the BGA?
I'm not sure I understand the question, but you mean are you tying the ground to the ground plane, but through a via, but a little further away? you know, you want to minimize the amount of time that the signals are not consistent and not you know, having the same impedance characteristics, right? So what you want to do is you want to, yes, tie the ground planes as soon as possible to your other planes. Again, what you're doing is isolating in between signal traces, so tie those as soon as you can to the plane.
All right, thank you, Mark. We'll move on to another question here for you. Could you use a via as a BGA pad to take the signal straight down to the strip line?
Sure. Yeah, I mean, that's a common one too. They call it a via in pad, I believe, a VIP. So that is a common practice now, as opposed to having some kind of breakout to a via down to a trace. So the via in pad is a very common practice, and yes, again, minimizing the amount of stubbing and trace that's hanging off of the actual via itself. So that's a really good thing to do, and I think it's not as expensive anymore. It's a very common practice.
All right, thank you, Mark. It looks like we have time for just one final question for you. On slide 21, could you please clarify what you meant that you mean 1 millimeter as you stated 1 mil?
No, I'm sorry. No, it's 1 mil. It's 1 mil thousandths of an inch, I guess. You know, it's not a meter. Yeah, there's a mixture of terms used in PCBs, millimeters and mils of millinches. So, yeah, 1 mil is again just a very common able. I'm clicking back, and I apologize if I'm creating headaches for anyone. 21, you said?
Yes, you're on it.
What? I'm on it. I don't think. Yeah, this was an RX. Yeah, okay. Yeah, I think it might even be back here. 1 mil. Yeah, it's 1 mil is recommended for the 28 gig. So it's a smaller, as small as possible, to try and keep the differential between the N and the P.
All right, thank you, Mark. Well, that looks like all the time that we have for questions for today. I'd like to thank Mark and Gus for a great presentation and Q&A session. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. Within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, if we did not get to your individual question today, someone will be getting back to you after the program is over. We'd like to thank you, our audience, for attending today's webinar, High-Speed Board Design Guidelines, brought to you by Tech Online, MoSys, and Arrow, and this webinar is copyright 2021 by AspenCore. The presentation materials are owned by or copyright by Tech Online, MoSys, and Arrow, and the individual speakers are solely responsible for their content and opinions. On behalf of our guests, MoSys and Arrow, I'm Chris Keach. Once again, we'd like to thank you for joining us, and we hope you have a great day.